Hello and welcome to Dr. Jim's Structures class, where we do structures by example.
Man's practicing fuzzy math again.
Thanks for tuning in. This is the fourth video on example 1 from Dr. Jim's video series on bending in beams and frames. These days, structural analysis is almost invariably computer-based. This video provides an easy-paced introduction to computer-based structural analysis by showing how the frame analysis program LinPro can be used to analyse the beam from example 1. Here's what LinPro looks like, and here's example 1, a simply supported beam carrying 2-point loads. Making safe and efficient use of structural analysis software requires a sound understanding of how structures work. In the previous 3 videos, example 1 was solved using hand calculation, and hand calculation is a good way to build your understanding of structural behaviour. If you'd like to watch the hand analysis videos before watching this one, click the link on the screen. So, what is LinPro? LinPro is a frame analysis program written by Enis Slijek, who I think is Bosnian. LinPro can be used to perform static and dynamic analysis of 2-dimensional beams and frames. LinPro is free, lightweight, graphical, and is easy to use. And Dr. Jim thanks Enis for his work, his skill, and his generosity. LinPro originated as a Windows program, but there is now also an Android version available from the Google Play Store. Dr. Jim's Structures class will use the Windows version. Dr. Jim recommends that you download a copy of LinPro for Windows from the web, or get yourself over to Dr. Jim's website at drjimstructures.com and download a copy from there. There's a link to Dr. Jim's website below. LinPro uses the finite element method to analyse structures. Finite element method is a numerical technique used to solve certain classes of partial differential equations. Yes, really. When applied to structural systems, the finite element, or FE method, is often referred to as the stiffness method and sometimes as the displacement method. But we'll not get into that right now. In simple terms, what you need to know is this. The stiffness method is used to analyse mathematical models of complex structural systems. These complex systems are built from simple structural elements, and that's the key. Simple elements whose behaviour is understood are connected together to build complex structural systems, and the complex systems are then analysed using the stiffness method. Applying the stiffness method requires 5 steps. 1. Define points in space using nodes. 2. Define elements or members in terms of these nodes. 3. Model supports by applying displacement conditions at nodes. These restraints are sometimes referred to as boundary conditions. 4. Define loads at nodes and on the elements. 5. Run the analysis. LinPro has both graphical and keyboard input capabilities. In this video, a model of example 1 will be built using keyboard input. LinPro's graphical input capabilities will be covered in the next video in the series. Dr. Jim thinks graphical input is the way to go, but you will have to decide what works best for you. And don't be afraid to experiment. You can't really break anything. Before starting, let's do some preparation. Firstly, check that the units are a good fit for the problem in hand. LinPro offers 4 choices for units. The default is kilonewtons and meters, and that's just fine for example 1, so that's what we'll use. Secondly, set up a grid appropriate for the structure to be analysed. A 14 by 2 metre grid will be used, and the beam will be built at a height of 1 metre. Note, the height at which the beam is built does not matter. To set up the grid, click the grid button type in 14, tab, type in 2 and close the dialog box. The background colour and size and colour of the grid dots makes the grid a little difficult to see. Dr. Jim has not discovered a way to change these, but we can live with what we have. And finally, to make the text on the diagrams more legible to YouTube viewers, that's you, the font size will be increased to 14 point. First step in building a structure is to define the nodes. Nodes are simply reference points in space. Nodes allow us to define structural elements, supports and loads. Click the Coordinates and Supports button to open the Coordinates dialog box. And don't be confused by the fact that LinPro refers to nodes as coordinates. Nodes and coordinates are the same thing. While defining the nodes, you should take the opportunity to also define the restraints. Restraints are also known as supports or boundary conditions. Notice that LinPro supplies the node number. Simply tab from box to box, type in coordinates. The support boxes are checked by hitting the spacebar. No need to reach for the mouse. LinPro draws the nodes and supports as they're entered, and that's great, as we can see at a glance if a mistake has been made. It's like magic. Once all the nodes have been entered, click the Members button to open the Members dialog box. The elements are defined by specifying the nodes at the ends of each member. Simply tab from box to box to avoid reaching for the mouse. Again, LinPro draws members as they're defined. Note that by default, all members are initially defined as type 1, so click on the Cross Sections button to see the properties of type 1 elements. These properties can be changed and additional member types can be defined. Notice that the cross-section dialog defines material as well as geometric properties. As we have no information regarding the material or the geometric properties for the beam, we'll simply accept the default values. However, if you're curious, and good engineers are curious people, click the link on the screen to see Dr. Jim reverse engineer LinPro's default element. It's fascinating. So what's left? Loads, of course. Click on the Loads button to open the Loads dialog box. LinPro supports 4 loading types. Most likely you will use only point and distributed loads, but notice that temperature and support settlement loading types are also available. Example 1 involves only point loads, so click on the Point tab. Point loads can be applied using global or local coordinates, and clicking the Hint button gives more information about the two systems. You might find it helpful to think of global as a coordinate system based on the structural axes, and local as a coordinate system based on the element axes. There's no way to define an inclined load in LinPro, so the 50 kN load at B, node 1 in our LinPro model, must be split into its components before it can be applied. The horizontal component is 30 kN to the right, that is plus 13 kN in the global X direction. Define the 30 kN load, then apply it to node 1. Notice that LinPro shows the loads graphically as they are defined. More magic. The vertical component is 40 kN downwards, that is minus 40 in the global Y direction. Define the load and again apply it to node 1. But look at that 40 kN force. It's showing acting downwards, that's good. It's the direction it acts in after all, but it has a negative sign. That's not so good. In fact, Dr. Jim thinks it's plain wrong. The negative sign reverses the load direction, so logically minus 40 kilonewtons acting downwards is the same as plus 40 kilonewtons acting upwards. What you need to know is that LinPro always shows the forces in the direction they act. So Dr. Jim's advice is to ignore any negative signs on graphical representations of loads and reactions. Now complete the loading by adding the 25 kN force at node 3. Is that all? Yes, Dr. Jim thinks it is, so click the green arrow to run a static analysis. It's super quick and the display changes to show the deflected shape. You should always ask yourself, does the deflected shape look reasonable? In fact, Dr. Jim recommends that you sketch the deflected shape before running any analysis. That will help you build your structural understanding. Be aware, the numerical values of the deflections are not meaningful here because we use the default member properties. To obtain meaningful deflections, we would have to know and use the actual material and geometric properties of the beam. Next, click the M button to show the bending moment diagram. It agrees with our hand calculations. Woohoo! Now click the T button to show the shear force diagram. It too agrees with our hand calculations. Things just get better and better. The N button shows the axial forces and the R button shows the reactions. These again agree with our hand calculations. Remember, we should ignore negative signs when looking at graphical representations of loads and reactions. So ignore the minus sign on the horizontal reaction at A, node 0. The arrow is pointing in the right direction. The negative sign should be simply ignored. The white button to the left of the green analysis arrow shows the structural layout, and the button to the right of the green analysis arrow gives access to tabular results. And clicking it opens a dialog box showing the reactions at the supports, and there's a tab that gives displacements at the nodes. There's also a tab giving the member end forces. Note the drop-down box that allows member selection. And finally, there's a tab for the internal member forces at 11 points along the selected member. 11 points because the member is divided into 10 equal lengths. Take time to have a look at what is available. Well, that completes the analysis. Notice how quick and easy and accurate computer analysis is compared with hand calculation. Unfortunately, to make safe and efficient use of structural analysis software requires a sound understanding of structural behaviour, and hand calculation is one route to developing that understanding. If you'd like a copy of LinPro, then get yourself over to Dr. Jim's website at drjimstructures.com. There's a link below. Well, thanks for watching. If you found this video useful, please give it a like and feel free to comment. Your feedback is appreciated. So bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.